Alright, so let's recall what we have done so far in this section. We proved this, that if I is a bounded interval and f is a uniformly continuous function on I, then f is Riemann integrable. And this led to the corollary that if this bounded interval turns out to be a closed interval and f is just continuous, then by a previous result, such functions are also automatically uniformly continuous, and hence again we have Riemann integrability. However, and in fact this we saw in the previous video itself, that if this interval is not a closed bounded interval, but say some other type of interval, then even if the function is continuous, Riemann integrability is not guaranteed. For example, we know that this function is continuous on this interval, but it's not bounded, and that's why it's not Riemann integrable. You cannot even ask the question whether it is Riemann integrable or not, because it's not bounded, and Riemann integrability has been defined only for bounded functions. However, if we say assume continuity and boundedness additionally, regardless of what the interval is, then we retain Riemann integrability. That's what we are going to see today in the form of this proposition. So in this proposition, I is a bounded interval and f from I to R is a function that is continuous and bounded. We are no longer talking about uniform continuity or anything. We have ordinary continuity of the function f, but we also have boundedness. So that function doesn't come under this condition, okay, because that is continuous but not bounded. Then f is still Riemann integrable. So let's see how we can prove this. So we will first see in the proof what happens when the interval is degenerate, and in that case the claim is true in a trivial manner. So the proof starts off like that. If I is, and there are two types of degenerate intervals, one of them is the empty set and the other one is a singleton set. Or I is, say, this. Instead of writing these things, you can write in words also. If I is a degenerate interval, then the claim is trivially true. Where A is a real number, then the claim is trivial or trivially true. Okay, so now we can assume that I is a non-degenerate interval. That means it does not have zero length, it has a positive length. Now let I be a non-degenerate interval. In fact, let I be one of these closed open interval a comma b, open closed interval a comma b, or open interval a comma b. Why are these three forms only enough? Why are we not considering the closed interval? Well, that's because we already have that result for the closed interval. I mean, it was the corollary to the previous result that we did in the previous video, that if our interval is closed and the function is continuous, then it's Riemann integrable. And boundedness, although it's separately given, but in that case continuity itself implies boundedness because it is uniformly continuous since the interval is closed. So there is no need to consider that case. And in fact, the author hasn't also said anything about that case in the proof because it's understood. No, we already have our claim for the case where I is the closed interval a comma b. Oh, we need to also mention what a and b are. Where a and b are real numbers such that a is less than b. This inequality ensures that our interval I is non-degenerate and has the positive length b minus a, regardless of which one I is. Okay. All right. Now we are going to use the fact that f is bounded. So it will have a bound which is a positive real number, since f is bounded. So there exists a positive real number m such that minus m is less than or equal to f of x, which is less than or equal to m for all inputs, that is all x's coming from our domain I of the function f. Now choose a positive real number epsilon that is less than or equal to b minus a divided by 2. Okay. Why are we able to choose this epsilon? That may be a question. Well, note that this inequality tells us that b minus a is positive. So b minus a divided by 2 will be even less than that. Still positive. And that is why you can of course choose some epsilon which is positive but less than this. And this epsilon actually, you see, this is, you should not think that this epsilon is in the sense that there exists an epsilon. It is your choice. You can change this epsilon at your will. So actually the nature of epsilon here is arbitrary. Like how epsilon is normally chosen, epsilon is something that can change. Okay. And then depending on that epsilon, something will happen. So it's not to be interpreted as a single epsilon which has been chosen that satisfies these inequalities. I mean, of course, epsilon does satisfy these inequalities, but we can change this epsilon and we will. okay, at the end of the proof. All right. Now, since, okay, so now we bring back that part of the hypothesis which says that f is continuous. Boundedness of f has given us this bound, but now we see what we get from continuity. Since f is continuous on I, its restriction on this closed interval a plus epsilon comma b minus epsilon is also continuous and hence is Riemann integrable. Okay. Now let's justify one thing at a time. Because f is continuous on I is the domain of f. So if we restrict f to this subinterval, then the restriction is also continuous, because if you restrict any continuous function to a smaller domain, which is a part of the original larger domain, then the restriction is also continuous. This is one of the properties of continuous functions. But this is a closed interval now, on which the restricted function is continuous. And so this will be Riemann integrable by what? By that corollary. And that corollary is in fact 1152. So within parentheses we write by corollary 1152. Okay, but there may be a slight confusion about this interval. Is there any confusion that this is a subset of I? Let's address that confusion. We have said that if we are restricting f to this, that makes sense only when this is a part of I. That is, if this is a subset of I. Now keep in mind that I can be of three forms. I can look like this. I can also look like this. And I can also look like this. No matter what I is among these three, this is going to be a subset of I. Why? Well, that's because a plus, okay, let me write it this way. A is less than a plus epsilon. Okay. A plus epsilon is less than b minus epsilon. Is it? That's a question. Okay, we are coming to that. But b minus epsilon is definitely less than b. So our interval, whatever it ultimately becomes, because we are yet to see this middle inequality, we are yet to justify that. Depending on whether this inequality is true, this will be a non-empty interval or maybe empty. We don't really know at this stage. But at least we know that a plus epsilon is greater than a and b minus epsilon is less than b. That's because epsilon is positive. And that is why this closed interval actually is a subset of this open interval itself, which in turn is a subset of both of these intervals. So in any case, no matter what I is, I may be this or this or this is a subset of I. So it makes sense to say that the restriction of f to this, okay, is also continuous. But now let's come to this inequality. Is it true? Let us see what this inequality is equivalent to. A minus epsilon, A plus epsilon is less than B minus epsilon if and only if. Let us add epsilon to both sides and subtract A from both sides. That will give us this. Double implication means we can go from this to that and we can also come back from that to this. And this is equivalent to this. Okay, so and we have that. And that is why from this condition itself we have this. And that is why not only do we have this closed interval as a subset of I, but it's in fact a non-degenerate interval. The left endpoint is really less than the right endpoint, so it has a positive length. Okay, so there is no problem with having this thing. Alright, so the restriction, we don't really know whether f is itself Riemann integrable on the whole I. In fact, that's what we are going to prove. But at least we get from that corollary that if we restrict f to this, then that also is continuous and hence it's Riemann integrable. Now, Riemann integrability of the restriction on this smaller interval will give us something now. What will it give? So for that we will go back to our definition of Riemann integral itself. So what we are saying is this. So we need to do some more rough work. We are saying that this thing a plus epsilon comma b minus epsilon f, this integral exists. It exists means what? It is equal to the upper Riemann integral also and also lower Riemann integral. The lower one we are not considering right now. Let's think of the upper integral of f restricted to this interval, and it exists. And it is what? It is the greatest lower bound of integrals of some functions star, where star is piecewise constant on this interval and majorizes f on this interval. This is the meaning of the upper Riemann integral. It is the greatest lower bound of this set. Now, what we do, if we add epsilon to this, already this was the greatest. Now, adding epsilon makes it even greater than that. So, it will no longer be a lower bound of this set, which means that at least some element from this set will be less than this quantity, right? That means there will exist a function h on this interval which is piecewise constant and which majorizes f on this interval and such that the integral of h on this interval is less than this f on this interval plus epsilon. Okay, so such a function will exist, and note also that this function has this subinterval as its domain, not the entire I. Okay, so this was the rough work. So now we are going to write that. And in fact, because everything, the actual proof kind of stopped there, so we can write from here. Okay, now, so because f on this interval is Riemann integrable by that corollary, hence there exists a piecewise constant function h which is like this, that majorizes f. If you simply write majorizes f, that's not enough, because f has domain I which is larger than this interval. You have to write majorizes f on this. Such that this inequality. We cannot write the entire thing here itself. It will look messy. Instead, let's write like this. Nicely and clearly, taking enough space. H. So H is PC and this is less than the integral of f plus epsilon. Actually, it's upper Riemann integral, but because f is Riemann integrable, we can just simply write ordinary integral itself. This is one inequality. So we can also get a similar inequality if we instead consider the consider this itself as the lower Riemann integral, which is true. It is also simultaneously the upper Riemann integral and lower Riemann integral. That, however, is the least upper bound of some set. So in that case, you will have to subtract epsilon to get something. We are not following that route. Instead, now what we are going to do, we will use this h to construct or to define a piecewise constant function, but now on the entire interval I, like this. Now, define h. Oh, sorry, h is that one itself. So let's give it the name h tilde on I by this rule. H tilde value at x is, it's going to be a partly defined function, is just h of x if x belongs to the domain of h. Otherwise, it's defined to be m, and m is that m, the bound of our original function f. If x belongs to the complement of that interval in I, okay. Now, on this interval, oh, and one more thing. Now, before we say something about majorization or anything, let us first of all note that this h tilde itself is a piecewise constant function. Why? Because on this interval, it is nothing but h, and h is piecewise constant. So, on different parts of the interval, it has constant values. Outside this interval, in capital I, also it is constant actually, which is constantly m. So, as a whole, h tilde is in fact a piecewise constant function itself. Note that h tilde is PC. Okay, so we understood how it is a PC function, but additionally it now majorizes f on the entire interval I. How? See, h already majorizes the restriction of f on this interval, and on this interval h tilde is nothing but h. So, in this part h tilde majorizes f. Outside also h tilde majorizes f, because outside h tilde is capital M, and already all the f values are less than or equal to capital M. So, that is why. And majorize, what happened to my set? Majorizes f, for emphasis we write on I. Okay. Now, let us calculate the integral of h tilde. Because h tilde is a function with domain I, so the integral will be over I. Now, the integral of h tilde over I. Okay, and in doing so, we are going to use one of the properties of Riemann integrals. Which property? Actually, it's theorem 11 to 16. It is that property which tells us that if you say have one Riemann integrable function f from I to R, the last one, I think it is part H or G, something like that, I don't exactly remember. And what you do, you partition I into two subintervals k and j. Then the restrictions of f to k and j themselves are Riemann integrable, and you can write the integral of f on I as the sum of the integrals of the restrictions of f on j and k over j and k respectively. This one, maybe we will have to use it 2 times to calculate the integral of this. Let's see how. Shall I keep this? But this is understood, now we can just get rid of this. I mean, this is what we are going to use now. But how are we going to partition our I? We are going to partition our I in this way. You see, this is our I. Oh, not like this, sorry. not like this, it's the real line of course, it has no gap. Say this is our A and this is B. Now we don't exactly know whether these endpoints belong to I or not, because I can be of three types. But that's we don't care. We do have this A plus epsilon and B minus epsilon. Okay, so this interval is going to sit somewhere between A and B like this. So there is a portion that is really outside this interval and lies to the left of this middle interval in I. I mean, this entire thing is I. And there is also a little portion to the right of this middle interval. And they will be there because epsilon is positive, A plus epsilon, no matter how small epsilon is, A plus epsilon will lie to the right of A. It may be close, it may be far away, we don't really know, but there will always be some region to the left of this middle interval and some region to the right of it inside I. So what we are going to do, we are going to write this integral as a sum of three integrals, one of which is the restriction of h tilde on this to this interval. Another one will be the restriction of h tilde to this interval, and the other one will be the restriction of h tilde to this interval. So let me keep this figure itself. Yeah. And let me also keep the definition of h tilde because we are going to need it. All right. Now, it's written slightly differently in the book because the author naturally first writes this integral over this region, plus integral over this interval, plus integral over that portion. But I am going to write the integral over the middle interval first. And over this interval, h tilde is actually h, because it's just that. So we write h. Okay. Keep in mind that we are now working with piecewise constant functions. There is no f here anymore. This is piecewise constant, that is also piecewise constant. So they are Riemann integrable. But now plus. What will be the integral of h tilde over this region? Over this region, note that h tilde is constantly n. It is a constant function. So that constant times the length of this interval, which is what? Epsilon, because a and a plus epsilon are the endpoints of this interval. And note that that fact is not going to be affected by whether a belongs to I or does not belong to I. Length is unaffected, epsilon, plus the integral of h tilde over this region also similarly is going to be m times, because there also it's constantly m, times the length of this interval, which is also epsilon, because the left point is b minus epsilon and the right point is b. B minus epsilon is plus epsilon. Okay. So we get this. Plus 2m epsilon. All right. Okay. However, we have already got one inequality, right? You remember that inequality, which in fact links the integral of h with the integral of the restriction of f on this. Now let's recall that inequality. Let me recall it here. What was it? It was this. Is less than so that means now in place of this h integral I can write this plus epsilon, so an inequality will appear. That means this thing will be less than f 2m epsilon plus epsilon is 2m plus 1 times epsilon. Okay. Now, what have we achieved here? You see, this is a piecewise constant function h tilde which majorizes our original function f, and its integral has been estimated like this. It is less than something. Now, if you think of the upper Riemann integral of f itself, let us think of the upper Riemann integral of f on I. By definition, this is the greatest lower bound of integrals of star, where star is PC and majorizes f on I. So, do you not think that this quantity is an element of this set? H tilde is also PC and H tilde also majorizes f on I. Yes, this is a legitimate element in this set, and this by definition is the greatest lower bound of this set, and that is why instead of starting with this, we could have started with this. That would give us this thing. Because it's GLB, it's after all an LB, a lower bound, and this is less than or equal to this, which in turn is less than this. So, actually I should write this so here, yeah, because this will look strange. I mean, this is the continuation from this here, and now we go to that part. So, the upper Riemann integral of f is less than this quantity. Plus 2m plus 1 times epsilon. Similarly, if one instead worked with lower Riemann integral, one would get this. In fact, it's advisable that you go through the details of this similar part, and try to write it in detail, everything. That means whatever we did here, there will be a parallel calculation, all the steps. Similarly, the lower Riemann integral of f will be greater than, here everything will be kind of opposite. The integral of this won't change, but here however, I mean, because this is already an integral that exists, f is Riemann integrable on this, but in this inequality, its interpretation is that it's the upper Riemann integral of f on this interval. Here it is the lower Riemann integral of f on this interval. But in this case, along with that, you get minus of 2m plus 1 times epsilon. And now we can use these two inequalities to see what the difference of this upper and lower Riemann integrals of f is. And that's what we want. From these inequalities, we get the upper integral minus the lower integral. When you write the lower integral, no, write the I a little above that, otherwise it may look like minus I. Minus I by itself does not have any meaning, but it can cause unnecessary confusion. Now, because f is bounded, we already know that this quantity is non-negative. And now it is, let me show the step also. Plus 2m plus 1 times epsilon minus because that was already minus and we are subtracting, so this now becomes plus 2m plus 1 times epsilon, and this quantity becomes equal to 4m plus 2 times epsilon. So you see that this non-negative real number has to be strictly less than this quantity. And this is where we are going to now need the fact that epsilon is arbitrary. That's why I said in the beginning that epsilon, it's not like it is just something. It can change. And because it can change, this cannot be positive. Because if this quantity is positive, then using that, you can choose an epsilon so small that this inequality will be violated. But that cannot happen, so that is why it cannot be positive, but it's non-negative, so it has to be 0. So we simply write, I mean, in such situations you just write since epsilon is positive, don't forget to mention that also, is arbitrary, we must have the upper Riemann integral minus the lower Riemann integral equal to 0. So they are equal. Hence, f is Riemann integrable. So if we additionally impose the condition that a continuous function is also bounded, then it ends up being Riemann integrable if it is over a bounded interval. Does not matter what the type of the interval is. So that's the end of the proof. Now depending on this, already we have got a large class of integrable functions. In the previous video itself, the corollary that we saw already gave us many integrable functions, but now the class has been enlarged even more, because that corollary only allows us to consider functions which have a closed bounded interval as its domain. Okay, so only such functions which are continuous and have a closed interval as their domain, they are Riemann integrable. That much we were able to prove. But now continuous and bounded, but the interval can be of any type, they are also Riemann integrable. Now if I prematurely say that trigonometric functions are continuous, which is something we already know, but we haven't really got to that stage where we can prove this fact. It will come afterwards, but for now, if we assume the fact that trigonometric functions are continuous and bounded, not all of them are bounded, but say the sine function is bounded, then using what we proved just now, you get this fact, say that if you define a function like this, say -1, 3 to r, such that, let me make it a bit more complicated, sin x plus cos x. Cos x is also continuous, sin x is also continuous, so their sum is continuous. Both of them are bounded, so their sum is also bounded. This function will be Riemann integrable, and its integral, that means it will be something we don't know what the value will be, but it will be a real number, it will exist because of this result. These things can be further extended to prove, which I in fact mentioned towards the beginning of this section itself, that continuity itself may not be there. It need not be there. That condition itself can be relaxed a little, and instead of a continuous function, we can talk about piecewise continuous functions. They also turn out to be Riemann integrable. That, however, we will see in the next video. So let me just end the things here itself for tonight, and tomorrow also there is an upload. What shall we do tomorrow? We have two things now. On Mondays we either do number theory or we do class 11 mathematics, because we already have done number theory the previous Monday. So let's do class 11 mathematics tomorrow. That is where we are doing trigonometric identities right now. So let's do that. So that's just it for tonight. See you tomorrow with trigonometric identities. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.